Hello everyone, welcome to the ninth part of 8051 microcontroller, that is instruction set 2, arithmetic instructions. These instructions performs arithmetic operations like addition, subtraction, multiplication, division, increment, decrement, etc. Let's see what mnemonics are contained in this instruction set. First is add C, that is add with carry, subtract with borrow, increment, decrement, mul used for multiplication, div and DAA, that is decimal adjust accumulator after addition. Let's see all these mnemonics in detail one by one. So before going to these mnemonics, the two instructions, that is add and subtract, that affects the 3 bits of PSW register. So first bit that is affected by this instruction is carry flag. It is set to 1 if there is a carry out of bit 7 but not from bit 6 during the addition or a subtraction. Next flag is auxiliary carry flag is set to 1 if there is a carry out of bit 3. Overflow flag, it is set to 1 if result of addition is greater than FFH or the result of addition is greater than 8 bit. So let's see the first mnemonic, that is add. Syntax is add a comma source byte. For all the arithmetic instructions, destination operand must be an accumulator. Function performed by this instruction is addition. So this instruction adds content of accumulator with a source and stores result into accumulator. Source is either immediate value, it may be a register, it may be a direct or register indirect address. So during execution of this instruction, overflow flag, auxiliary carry flag and carry flags may be affected. Let's see the examples. First example is add a comma hash 25h. So this hash sign preceding 25h indicates that this is a immediate value. So this value, that is 25h, gets added with the content of accumulator and the result will be stored into the accumulator. Next example is add a comma R2. So here content of register R2 gets added with the content of accumulator and the result will be stored into the accumulator. Third example is add a comma @R0. So here @ sign indicate that this R0 is used as a pointer. So the content of the memory location to which this R0 is pointing gets added with the content of accumulator and the result will be stored into the accumulator. Next example is add a comma 40h. So no hash sign is preceding to 40h indicate that this is direct address. So the content of this memory location gets added with the content of accumulator and the result will be stored into the accumulator. Let's see the example in detail. So here the first instruction is given, move a comma hash 3fh. That means this instruction copy the value 3fh into accumulator. And the next instruction add a comma hash 13h. So this instruction adds the content of accumulator with the value d3h and the result will be stored into the accumulator. So let's see what happens after execution of these instructions. So after execution of a first instruction, content of a becomes 3fh. So it is represented in binary as 0011 1111. It gets added with a 13h in second instruction. So 13h is written in binary 0001 0011. So let's see what happened after execution of this second instruction. So here this column gets added, that is 1 plus 1. So we get the sum 0, 1 carry. In second column we have to add 1 plus 1 plus 1. So here we get sum 1 and 1 carry. Again in the next column we have to add 1 plus 0 plus 1. So we get sum 0, 1 carry. Again, in third column, we have to add 1 plus 0 plus 1. So sum 0, 1 carry. So look here, the carry is generated, this carry is generated from bit 3 or from third column for a fourth column. And that's why the auxiliary carry flag will set to 1. Now, the addition of this fourth column is sum 1, carry 1. If we add this carry to the next column, we get 1 plus 0 plus 1 equal to 0, 1 carry. So here, we have to add 0 plus 0 plus 1. So sum is 1 and no carry is generated for the 7th column. So we are adding 0 plus 0 is 0. So we get the answer as a 52H. As no final carry is generated or no carry is generated from the 7th column or 7th bit, that's why the carry flag is 0. And the result of this addition is not more than FFH or it is not greater than 8 bit. So the overflow flag is equal to 0. Next instruction is add C, that is add with carry. So syntax for this instruction is add C a comma source byte. So this instruction add the source byte with a carry. So this instruction adds content of accumulator, carry flag and source byte, then stores result into accumulator. And the source is either immediate value, it may be a register or it may be a direct or register indirect address. And during execution of this instruction, overflow flag, auxiliary carry flag and carry flags may be affected. Let's see the example. So first example is add C a comma hash 25H. So here the content of carry, then content of source byte and content of accumulator, they get added and the result will be stored into the accumulator. Next example is add C a comma R2. So here content of the carry flag gets added with the content of register R2, gets added with the content of accumulator and the result will be stored into the accumulator. Next example is add C a comma at the rate R0. So here again R0 is used as a pointer. So the content of carry flag, then content of the memory location to which this R0 is pointing and the content of accumulator gets added and result will be stored into the accumulator. Next example is add C a comma 40H. So here the content of carry flag and the content of memory location 40H gets added with the content of accumulator and result will be stored into the accumulator. Let's see the example. So here again we are moving or copying the value 3FH into A and we are adding the value D3H into accumulator. So after execution of these instructions, so A will contain 3FH, it gets added with the value D3H and the content of a carry flag, that is 1. So after addition, the result will be 13H and as the carry is generated from the third column, the auxiliary carry flag will be set. Again final carry will be generated and that's why the carry flag will be set. As the result is less than 8 bit, so overflow flag is 0. Next instruction is subtract with borrow. So the syntax is sub a comma source byte. Function is subtract with borrow. So this instruction subtracts content of a source byte and carry flag from accumulator and then stores result into the accumulator. So source is either immediate value, it may be a register, direct or register indirect address. So during execution of this instruction, overflow flag, auxiliary carry flag and carry flags may be affected. So let's see the examples. Subtract a comma hash 25H. So here the content of carry flag and the source byte, they are subtracted from the content of accumulator and the result will be stored into the accumulator. Similar examples they have taken as subtract a comma R2, then subtract a comma at the rate R0, and subtract A, 40H. So here in comment the operation is specified. So let's see one example in detail. So first we are moving value 0C9H into accumulator, and now the second value 54H we are moving into register R2, and the third instruction is subtract A, R2. That means we are subtracting 54H from C9H. So let's see what happened after execution of the second instruction. So A contained the value C9H, it is, and the register R2 contained the value 54H, and here the borrow, that means carry flag, contained the value 1. We get the subtraction, that is 74H, that is 0 1 1 1 0 1 0 0. So here no borrow is generated from fourth column to the third, that's why auxiliary carry flag is 0. No final borrow is generated, that's why carry flag is 0, and the result is not more than 8 bit, so overflow flag will be 0. Next mnemonic is mul, used for multiplication. Syntax for this is mul AB. So here the destination and source register, they are fixed and they must be A and B. No other registers we can use in this register. So function of this instruction is multiply A with a B, or multiply content of accumulator with the content of a B. So this instruction multiplies contents of accumulator and register B and stores lower order byte of a result into accumulator and higher order byte of result into B. As after multiplication the result is more than 8 bit, that's why this provision is made, that is the lower order byte of a result stored into the accumulator and higher order byte of a result is stored into register B. So in this instruction carry and overflow flags are always clear. So let's see the example. Let A equal to 50H, that is nothing but the decimal value 80, B equal to 0AH, that is equivalent to decimal value 160. So after execution of this instruction, that is mul AB, result is 3200H, that is 12,800. So result will be stored as, that is the higher byte 32H, it will be stored into register B, and the lower byte will be stored into register accumulator. Next mnemonic is div, used for division. Again syntax for this instruction is div AB. Again in this instruction we have to use register A and B only. So here this instruction divide content of accumulator by the content of register B. This instruction divides content in accumulator by the content in register B and stores quotient into accumulator and remainder into B. So in this instruction carry and overflow flags are always clear. Let's see the example. Let A equal to 0 FBH, that is nothing but the value 251 in decimal, and register B contain the value 12H, that is 18 in decimal. Then after execution of this instruction, that is div AB, result is, that means the quotient is stored into the accumulator and remainder will be stored into the register B. So we get A equals to 0 D3H, that is nothing but a 13, and remainder that is equal to 11H, that is nothing but a 17. Increment. Syntax for increment is increment byte. So the function performed by this instruction is it increment byte or a source byte by one variable. So this instruction increments the indicated byte variable by 1, and during execution of this instruction no flags are affected. So let's see the example. Let R0 contains the value 7EH and internal RAM locations 7EH and 7FH contain value 0FEH and 45H respectively. So remember here we are using this R0 as a pointer. So this R0 contains the value 7EH. That means it is pointing to the RAM location, internal RAM location 7EH, whose content is nothing but a 0FEH, and the memory location 7FH, whose content is 45H. So let's see, after execution of this instruction, that is increment at the rate R0. So here, increment at the rate R0, that means it will increment the content of the memory location to which this R0 is pointing. Now, the content of R0 is 7EH, and the content of this 7EH is nothing but a 0FEH. So, it will increment the content of 7EH, that is FEH will be incremented by, that is equal to 0FFH. Next instruction is increment R0. It will simply increment the content of R0. So before execution of this instruction, content of R0 is 7EH, and after execution of this instruction, content of R0 will be 7FH. Again, increment at the rate R0. Now this instruction increment the content of memory location to which this R0 is pointing. Now the content of R0 is nothing but a 7FH. That means it will increment the content of memory location 7FH by 1. And the content of memory location 7FH is nothing but a 45H. And after execution of this instruction, it will be 46H. DEC, that is decrement. Syntax for decrement instruction is DEC, source byte. So it decrement byte by one variable. This instruction decrements the indicated source byte variable by 1. No flags are affected during the execution of this instruction. Let's see the example. Again here R0. Now R0 contains the value 7FH. That is nothing but the internal RAM location. And the internal RAM location, that is 7EH and 7FH, contain the value 0FEH and 45H respectively. Now, what happened after the execution of this instruction? So here R0 is nothing but a pointer. It is pointing toward the memory location 7FH, whose content 7FH, whose content is 45H, that is decremented by 1 after execution of this instruction. And that's why the memory location 7FH will contain value 44H. Again, in this instruction, we are just decrementing the content of R0. So before execution of this instruction, content of R0 is 7FH, and after execution of this instruction, content of R0 will be 7EH, that is decremented by 1. Decrement at the rate R0. So this instruction will decrement the content of memory location by 1 to which this R0 is pointing. So before execution of this instruction, content of R0 is 7EH, and this 7EH will contain the value 0FEH. So this instruction will decrement the content of memory location 7EH by 1. That means this content will decrement by 1 and it will get 0FDH. The next instruction or mnemonic is DAA, that is decimal adjust accumulator after addition. So the function of this instruction is decimal adjust accumulator after addition. So this instruction adjusts accumulator after addition to produce proper BCD digit. Actually, this instruction is used for BCD numbers addition. So if the nibble of the accumulator is less than 9 after addition, result is more than 9, then 6 is added into that nibble. So when the addition takes place between the two registers or two numbers, and then the result or the lower or upper nibbles, they are greater than 9, then 6 is added into that nibbles. Only carry and overflow flags are affected during the execution of this instruction. Let's see the example. So let A equal to 56H and R2 equal to 67H. So what happened after execution of the instruction, that is add A comma R2? What happened after execution of this instruction? Content of R2, that is nothing but a 67, that gets added with the content of accumulator, that is 56H. We get the result, that is 0BDH. If we write this hex number into binary, we get 10111101. If we concentrate to the lower nibble, that means lower 4 bits of the result, this is nothing but a 1101. So this is greater than 9. Again, this is the upper nibble, this is also greater than 9. So what this instruction will do, that is DAA, decimal adjust accumulator after addition. What this will do? This will add 6 to both nibbles, as both nibbles they are greater than 9. So this instruction adds 6 to both nibbles. So we get A equal to 23H, that is the perfect BCD number. Thank you.